Okay, so this is the question that Kendall brought me today. It's number 6 from a textbook, and it's about the researcher who hypothesizes that individuals who listen to classical music will score differently from general population on a test of spatial ability. So the hypothesis is that they will score differently. So that means they could score better, they could score worse. It doesn't indicate a particular direction. So we're going to interpret that as it could be either above or below what the general population does. So we're given that mu equals 58. So mu with no subscript means we have the mean of the population. So this is the mean of all test scores from the entire population of all people. Okay, and we're going to need that information. And we're given that a random sample of 14 individuals, so we have a sample with 14 individuals, so n equals 14, who listen to classical music. They take that same test, and their scores are given. So since we have this handy-dandy CAS calculator, one of the first things that I would do is go ahead and get the data in. So we have a really friendly calculator for that. If we do control document, that's your add page command, we're going to add a list and spreadsheet. That's number 4. And you have to name your variable. So I'm going to arrow up to the very top line of column A, and I'm going to call it, I don't know, it's a classical music, it's just some sort of a test. So we'll just say test. Now, as long as these letters stay italicized, it's not a reserved word, and we can do it. So this is their test scores. Okay, and I'm going to input those. So we start down here in the first white box. This second blank is for an equation to do a computation, and we're not going to do that. We're just going to put some data in. So we'll type in numbers, press enter after each one. It'll automatically temporarily save, and input all of our numbers. Okay, and so I'm double check that I've got 14, and it's always a good idea to double check input to make sure that we've not done anything goofy. So we just arrow up and down to double check that, because it would be a shame to make a mistake, to mess the whole problem up because we have a typo. Alright, so now that the data's in, we're going to be ready to use that to get some summary statistics in a minute. Okay, so part A asks if this is a one-tailed or a two-tailed test, and the key word to it being two-tailed is that in the original sentence it says the hypothesis is that individuals who listen to music will score differently, which means we could score lower or we could score higher, and either of those would be something significant if it's different enough. So differently tells me higher or lower, that's two-tailed. Okay, and that's not, I wish that would focus a little bit better. It may not get any better than that. Okay, part B, what are the null and alternative hypotheses? So the null hypothesis is your status quo. Nothing interesting is going on. So the null hypothesis would be that your that all of the people who listen to classical music will score the same as the people in the general population. So we're making a hypothesis that if people who listen to classical music have the same mean score as the population of all people. So we would hypothesize that the mean of, and I'm going to just go ahead and give it a subscript, the mean of, let's say, the music people, I'm going to let it be an M, that the mean of the music people is the same as the mean of the population, which would be 58. The alternative is that people who listen to classical music do not have the same score or score differently. So people who listen to classical have different scores than the population. So the mu for the music people is not 58. And you may or may not need a subscript. I'm not sure what the teacher would want, but sometimes it helps clarify that we're not talking about the general population, we're talking about a subset of the population. Okay, now we want to compute T of OB, what is that? T of OBT? I don't, okay. Am I supposed to know what OBT is? Okay, I'm going to have to Google that because I have no idea. Let's see. That is not something I have ever seen before. What is OBT in statistics? So, where OBT is the sample mean. Okay, that was about as clear as mud. That's just not a notation I've ever seen before. I'm still looking. Calculated test statistic. Okay, well, I think I know what that is. Let me look at one other thing. What is T of CV? Critical value. Okay, the notation is is messing with me a little bit here, so I may just have to fudge on notation for a minute because I'm not sure what the difference is between T of OBT and TCV. Although I think this is actually our test statistic, and the test statistic is going to be what you observe from your sample. So I'm gonna guess that this is from our observations. So that means I'm gonna go back here and get some summary statistics. So I'm going to go to menu. There's all sorts of cool tools in the menu, one of which is to calculate some statistics. And I've got an option to run some stat calculations, that's number 1, and do some one variable statistics, because I only have one variable, it's test scores. One list, so click on OK. And the X list is the list of test scores. So if I arrow to the right there, test is stored in memory, temporary memory, so it'll just bring that up. I can click on it, and then tab will get me through the rest of all these. Don't worry about any of the rest of those. All you have to do is pick the list that it comes from, so that's the first one. When you click OK, you get two things that are important. You get X bar, which is the mean of the sample. So the mean of this sample of 14 people is 59. So we take the observed sample mean first when we calculate a t-score. It's exactly like a z-score. You do observed minus expected, which is your mean. The mean is 58. That's the mean of your population that we started out here, over the standard deviation. And there's a formula for that. The standard deviation, let me put this over to the side. T is equal to the observed mean, x bar, minus the expected, and I didn't spell that right, expected, which is mu, all over the standard deviation, which is the standard deviation S of your sample divided by square root of n, which is your sample size. S, the calculator gives us. It's right here. It's 3.8028 something something something. If you arrow down and hover over it, you get more detail on the bottom. but 3.80 blah blah blah. Let's say this is 3.803-ish. We'll round to 3 decimal places. Divide by the square root of n, and the square root of n is square root of 14. So we need some formulas there. And then we have to crunch that. So I'm going to have to go back to a calculator page. So Control, add a page, and add a calculator. And if I do Control divide, notice there's a little division symbol there. And we can put 59 minus 58 on top. And on the bottom we can do 3.803 divided by square root of 14. And that's about 0.983, 0.98. It actually rounds to 4. So this is the t-score for our sample. So this tells us where on the t-distribution this particular sample lands. So I'm going to draw a quick picture. Your t-distribution looks like normal, but it has more variation in it, so it's a little more spread out. It's more fat and short than a z would be, than a normal would be. The mean of that is 58. The mean is what your population does. You want to know where 59 is. 59 is what you got from your sample. Well, it's almost 1 standard deviation above the mean, 0.98 standard deviations. If 1 standard deviation above the mean is here, that means your score of 59 hits about there. Okay, so that kind of is some perspective on what that number means. This tells me where on that t-curve our sample lands. Okay, so then we get to D, and D's throwing me just a little bit because they want the t of the critical value. So, and that's not really how we do things in my neck of the woods, but the critical value is dependent on how many standard deviations from the mean you want to go. So if you want, and it doesn't say here, I don't know what they're looking for. In AP statistics, more often than not, we use 95% confidence, or a 95%, let me try it this way. We say that if we're within 2 standard deviations from the mean, if the mean is here and we're within 2 standard deviations, that holds roughly 95% of all possible samples. And if we're in the outer 5%, that's what we call reject zone. So if we get a sample that's farther than 2 to the right, that's a reject, the null hypothesis. If we get a sample that's over here, since it's a two-tailed test, you got to look at both ends. If you get a sample that's this low or lower, you would reject your null. So I think what he's fishing for in D is how many standard deviations out from the mean you're willing to go. And so 1 standard deviation from the mean is what you have, roughly 1. That's not very unusual. That's not far enough away from the mean to be particularly interesting. So I'm a little fudgy on what we want there. If we're actually supposed to give a t-score for whatever cutoff we want to use. I just don't know for sure, and I'm about afraid to say, but okay, so what we could do, and this may be too much. If it is, just, fast forward or skip over it or close your ears. You have in your menu under probability and distributions, that's number 5, there's some t stuff there, and TCDF gives you cumulative density under a t-curve. What you can, that's not what I need, let me back up, menu, probability, distributions, inverse t will give you a t-score for a cutoff. So, and this may or may not be helpful, I'm just going to say that again. 6 is inverse t, and inverse t lets you give an area under the curve. 2.5% of all your area is out here, and 2.5% of all your area is here. So if you were interested in that being your cutoff, then you need the t-score that goes with it. So you can actually give the calculator the area under the curve here, which is 0.025, 2.5%. Degrees of freedom are 1 less than your sample size. So degrees of freedom are going to be 14 minus 1, or 13 here. And the degrees of freedom is related to your sample in that it tells you how skinny or fat this graph is, how much variation is in it. So we have a degrees of freedom of 13. So this t-score here is negative 2.16, which means this t-score up here is positive 2.16. So if you're going to reject, if you get a p-value of 5% or less, then you're going to want a t-score of 2.16. It could be that the t for the critical value of 5%, it could be you're looking for that 2.16, but I'm not sure. I'm just not sure, because this notation is not anything that I've used before, and this is not really how we handle it. In AP statistics, we actually calculate a probability, and then we make a decision based on the probability. So we kind of look at things a little bit differently. Okay, well, let's at least see if we can finish this thing up. So part D, or part E, says should H not be rejected, and I'm going to give a wholehearted no to that. So I'm going to say no, because this sample mean of 59 is less than 1 standard deviation from the mean. So it's definitely within this region of it's not very interesting, so we're not going to reject. You might argue that the t OBT from your observed sample is smaller than the t for your critical value, and that's your call. If the observed t is smaller than your critical value t, then you would not reject. If your observed t is bigger, that means you're outside the boundaries of what you want to allow. And I just realized that I should have scooted that up. That was so not helpful, because I'm not looking at my screen. But you're out of that allowable space of things are okay. So if t of OBT is bigger than t of CV, you would reject, and it's not. So we would fail to reject, and we would base that on the fact that part C is smaller than part D. So we should conclude that we have no evidence that people who listen to classical music score differently on spatial reasoning tests than the general population. And I'm not going to try to write all that. If determine the 95% confidence interval for the population mean based on the sample mean. Okay, so the confidence interval is computed by taking your statistic, which is your mean of your sample, plus or minus your critical value. Now, I'm still banking on this 2.16, and that's what I would use for 95% confidence, because that's what we computed here. So we call this T star, by the way, with 13 degrees of freedom. That's its label. I guess I probably should, let me back up. Confidence interval is X bar plus or minus your T star, and I think that's what they're calling T with the CV. They're calling this the critical value T, times the standard error, which is S over square root of N. So we know that the mean is 59. Oh, got off the paper again. Plus or minus the T star for 95% should be 2.16 times the standard deviation of the sample, which is 3.803 over square root of N, which is 14. So we're reusing this packet right here for this. And then you can crunch the numbers on your calculator, but you don't have to do all that work on the calculator because you have a cool little tool that does confidence intervals. If you go to menu and statistics, you have a confidence interval option, and this is a one sample T, so we're just going to do a T interval, so 2 is what we want. We can do it by data, or we can do it by this. Let me show you both ways. If you do it by data, you have to tell it what list to pull from. So we have our numbers in a list called test. Don't worry about frequency list, it's always 1, and your confidence level is 95%. You could change it, but you want 95 here. And it's going to give you your lower bound of 56.8 and an upper bound of 61.2. So we're 95% confident that the average score that people who listen to classical music make on this test is between 56.8 and 61.2. Now, you can run it another way. If you go back to Menu, Statistics, Confidence Intervals, and T-interval, instead of the data, you could change it to stats and give it the summary statistics. So let's try it that way and see how it looks. So you can give it the X bar, that's 59. You can do standard deviation of X, that's a 3.803. N is 14. It'll compute its own degrees of freedom from that. Confidence level stays 95%. And you'll notice that you get essentially the same thing for your upper and lower bound if you work it with your summary statistics. So you could go straight to this if you wanted to skip over some of those one variable stats we did earlier. Okay, I hope that was helpful. That's it.